This is going to be a precursor to what we're going to be doing on Friday. Give a little background, but we've done a lot of work of finding the value of the derivative at certain points to figure out how fast something is going, but we haven't looked at the actual graph of derivatives yet, right? So now that you guys know the power rule and how to do it with, rational functions, radical functions, and everything else, let's go back and just look at some of the basics of functions, 0 degree through third degree functions, right? And look at what the graph of the derivative actually looks like, and make sure we understand what it means. So this is going to be another one of those lessons that the answer, quote, what you write is very, very basic, but you understanding it is not. So if I ask you a question like, what's f prime of t? What is that? How do you interpret that? What does it mean? That's the answer to that question is way more than, okay, what's the graph? Right? So the understanding, again, is the priority here, not just an answer. Okay? So as you go through this, just follow along, make sense out of it. Don't distract yourself, do anything else that's going to be in your way. Right? And that way you understand what you're actually doing throughout all these. Okay? So first of all, we'll start off with the 0 degree functions, right? So f of x equals 2, or y equals 2, of course, is just a horizontal line. So recall that when we're doing a lot of these graphs, usually they label this as the f of x axis, and this is the x-axis, right? And then its derivative is going to be f prime of x, right? So the y-axis or vertical axis is actually f prime of x, while this is the same. So the x values here are identical when you're graphing, right? So the x values are always the same. So t equals 4 seconds on this graph is the same as t equals 4 seconds on this graph. It's just the y values tell you different things. On the problems on the f of x function, it tells you how far it's gone, like it's gone 80 miles, its position or distance, whereas the derivative graph or function is telling you how fast it goes. Okay, so recall that the f prime of x is also called the instantaneous speed. I can't spell right now, but speed. But don't forget that's the same as slope. So really, when you're doing these graphs, you're really just looking at the slope at each y value, okay? And that's the most important thing to remember, that this is kind of like the same thing of making a t-chart when you're graphing the function. You can just plug in a lot of points, find out what the y values are, and then connect all the dots, and you have your graph. It's kind of like what we're doing here. So what we're using the index card for is to line these up. So if you go to here, you can line up -4 on the top graph, the regular function, with -4 on the derivative function, right? And we can figure out how to graph this just by looking at these slopes. So all you're going to do, and this is going to look very weird at first, ask yourself at -4, what's the slope of that line at -4? Right, and don't overthink it. So just spit it out. What is it? 0. So that is now the answer for the y value. What used to be the y value here is now the slope. So remember, all these numbers are slopes. These are all slope values, right? Whereas you used to have to count up and over, up and over. Well, that number is now just what the y-axis used to be. That's what the derivative function looks like. So with any given function, you can just pick any values. Like I can go to t equals +2 and ask myself, what's the slope right here? And I figure out, well, of course, the slope of that is also still 0. So that's why I'm graphing t, 0 on the f prime of x graph. And you can imagine if you keep doing this, well, this whole line, this whole slope of this line is 0, so it's no surprise that the equation of the line is just 0. So you can make 3 points and just connect them and say, well, this is the graph of the derivative. Okay. Now we can also, and what's the equation of that line? All right. The equation of this line is going to be the same thing as the derivative of the function. So it's the same thing. That'd be a good matching question. Like, those two go together. So the equation of this line of f prime is going to be the derivative using the power rule here. So power rule just says this will be 0, right? And this is the equation y equals 0, or in this case f prime of x equals 0, because all of the coordinates are something comma 0, right? That's 2 comma 0, 4 comma 0, 6 comma 0. So all those have the same coordinate of 0. All right, do the same thing on the right-hand column. A lot of these I'll do the left and you do the right. If you feel like you already got it, go ahead and, graph them out. You could pick any points, it doesn't matter. You'll get the same thing. And the important thing to ask yourself is, well, does it make sense why I'm putting a dot here? Because this is going to be the slope at that particular point. Doesn't matter which ones you pick. Slope at that point, again, is 0. Slope at -3, again 0. And slope at +5, maybe, again 0. So I just picked 3 different points, asked myself, what's the slope at those 3 different points? And that became the, quote, y value, or vertical value here. So once again, you see the derivative is 0. Right? Samesies. So these have the same exact derivative graph. Now, can you extrapolate? What do you think the graph would look like if this was f of x equals 10, or 1,000, or -2 pi? Right? So really fast you can think, well, all those have a slope of 0, so they all will have the exact same derivative graph. So here's one of the big concepts you want to think about, is that derivative graphs are not unique. Meaning, if you take any equation and you take 1,000 other equations, they could all have the same derivative, right? So there's way fewer derivatives than there are original graphs, right? There's an infinite number of horizontal lines that are f of x equals just a number, a 0-degree function, right? They will all have the exact same derivative graph. And we'll get to, there's more stuff down here, increasing and decreasing intervals. We'll do that at the very end. So this is a 0 degree, right? These are 0-degree functions, means that they have no x values here. There's no x's in here, because the degree is the same as the highest exponent on x. So next we'll jump into, let's look at first-degree polynomials. And we'll just keep on going up to second degree and then third degree. So these are going to be first-degree polynomials, and we're doing this just to look for patterns so it makes sense, right? Not that we just get an answer, but that the answers make sense. So same thing. We can pick any value of x here. Let's say x equals, let's go to 2. And ask yourself, what is the slope of the line right there at 2? What's the slope of this line right here at x equals 2? And then you would say, what? Don't overthink it. Yeah, just 2, right? This has a slope of 2. So that's going to be the new y value, because we're graphing the slopes. We're plotting the slope. F prime means these are all slopes. So if you ever get confused, you're like, how do I graph f prime? Just think of, we have an x-axis and we have a slope axis. Now we're just saying, well, the slope at that point is 2, so at t equals 2, right? I'll plot a point at 2, because the slope is now 2. And then I can go up to maybe 4 and ask myself, well, what's the slope here at 4? And then you would say 2 again. All right? And I can go down to, -2. What's the slope at -2? And you would say 2 again. All right, and then as soon as you have 3 points, you got a nice little pattern. So it looks like the derivative, of a first degree function is a 0 degree function, right? This looks familiar. Well, why is that? Ask yourself, why is this? If you had to come up with a sentence, the reason why this is a horizontal line is what? The reason this is a horizontal line is why? Slope doesn't change. This slope doesn't change, and since we're graphing slope, it's a constant function. Right? This is called a constant function, meaning it's not going up and down, doesn't vary. Constant is opposite of varying or variable, right? It's just a number. So this hopefully makes sense on why a diagonal line would have a derivative that's a horizontal line. You want to make sense of that in your head. It's one of those questions that I can put out in words, but it's not like, we'll get the right answer and compute, but something you have to understand for it to make sense. All right, go ahead and do the right-hand side. If you want to, make a guess of what you think the derivative will look like, and then actually pick the points and prove it to yourself what that derivative is. By the way, this was 2. If all went according to plan here, you would get another horizontal line. No surprise, went from a first degree to a 0 degree. 0 degrees have to be just horizontal flat lines. They all ended up at -3 because the slope of this line at any point, every single point actually, is -3. And of course, if you use the power rule on this function, say what's the derivative of this function, you'd end up with just -3. This would be to the power of 1. 1 times -3. Drop it by 1. The 2 goes away. Same thing over here. So you can get these answers down here, the function answers, by using the power rule, or by actually physically looking at the graph, plotting points, and asking yourself, what's the equations of these lines? And it'll come out to the same thing. That's a nice little way to check your answer, by the way, if you're not quite sure. Like, did I do that right? Okay. All right, let's pump it up to second degree. Second degree, also known as quadratics. Quadratics. Which never made sense to me because quad is usually a prefix for 4. But yeah, it's a second degree. So don't get those mixed up. Now, anybody want to take a guess? What will the graph of the derivatives of the derivatives of these graphs look like? What type of? Do you see a pattern yet? What we've done so far? So always be looking for patterns. So derivative of this first 0 degree went down just a horizontal line. The derivative of a diagonal line, the second degree, was just a first degree. All right. So what will the derivative of a second degree look like? What degree will it be? It'll be a first degree, which means it'll look like, it'll be linear, aka a diagonal line. So we can already expect if we have parabolas, when we're doing the derivatives, they should come out to diagonal lines. Now, why are they diagonal all of a sudden? What happened? Well, if you look at this, the slopes here are changing. The slope here is different from the slope here, is different from the slope here. All right? These are negative, negative, This has a slope of 0, and these are positive. And that's even more positive. This is a smaller positive number than this one. This one is even more steep, so the slope is even bigger. So the slope is changing throughout the curved graph. So once you get to anything with a curve, you expect some ups and downs and no more of these flat lines. Now the easiest place to start is at the slope equals 0. Okay? So if you line that up and say, well, right here at this t, it looks like maybe 1/2, right? Right there, the slope there is 0. So I should have a point right there. Because at that t equals 1/2, let's say the slope is 0. And these are all negative slopes, right? So I expect to the left of this, the graph will be below here, right? All the negative slopes are down here. These are all negative slopes, and these are all negative slopes here. So I expect, because this is going down, I'm going to have the graph down here somewhere. And these are all positive slopes, so that part of the graph, when I get bigger than this point, right, these will be up here. And now it's kind of hard to estimate it, right? Like, well, what's the slope right here? We'd have to like draw this tangent line really out, and we have to, count very carefully, right? So all we're going to do is really just kind of cut to the chase and say, let's use the power rule here. So the power rule of the derivative here will be of x squared minus x minus 2 would simply be 2x. That's here. Derivative of negative x would be negative 1. So it'd be minus 1. And if you go ahead and graph that, start at negative 1, up 1 over 2. Do that a few times. You can see, sure enough, it graphs exactly as we expected. So all of this, right, these are negative slopes. Right? All of these are positive slopes. And they correspond with the fact that these are positive slopes here. That's why these are all above the x-axis, and these are all negative slopes, and that's why they're below the x-axis. So I can always tell when a function is decreasing, it'll just be below the x-axis. That's where all the decreasing would be negative slopes. It's going down, 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 hits 0 at the vertex, and then starts going increasing. Positive slopes, positive slopes. That's why those are graphed above the x-axis. So it's another way of asking yourself or figuring out, how do we know when a function is increasing or decreasing? Right? Well, if you look at its derivative, we can tell what's below the x-axis and what is above the x-axis. Right? So that's where this part comes in play. Right? We can see it's decreasing, right? aka below x-axis. Where is it below the x-axis? I'd say f prime is below the x-axis. So that would be starting here. Let's say that's 1/2. Let's just say that's 1/2 right there. So anything below 1/2, it's decreasing. And we can get this answer right here as well. We can see it's going down, it's going down, 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 down. We get to 1/2. It's not going down any further. So at 1/2 or less than, or to the left of 1/2, right, it's decreasing. Then it hits 0, and then right here, that's when it's increasing. It's above the x-axis. All right, so where is it above the x-axis? From 1/2 as you get bigger. And you don't want to use equal to's here, because equal to 1/2, it's actually 0. And if it's at 0, it's not increasing or nor decreasing. It's at a critical point, critical juncture there. All right, try that out on the right-hand side. Start with 0. Where is the slope is 0, and go from there. Of course, this is a negative slope. No coincidence that this is opening down. This has a negative. Right? So it's opening down. Its derivative has a negative. So it's going down. Which means initially it's increasing, increasing, increasing. So it initially starts with all positive slopes. Because these are all positive slopes up here. And then they get smaller, the slopes get smaller, 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 and they finally hit 0 right here at t equals 1, or x equals 1. And then we start going down, negative slope, negative slope, negative slope, negative slope, and that's why from this point on, these are all negative slopes right here. All the slopes or speeds are negative when it's falling. So what interval is it decreasing? Okay. Where is it below the x-axis here? From this point, as t or x gets bigger, that's when all the slopes or the speeds are negative. So it's decreasing from x greater than 1. Of course, it's increasing, it's going up, 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 for all the x's less than 1. And everything in math, you know, and I made a point of saying this at the beginning of the unit, you always want to think about reversibility. So like today in beginning of calculus, we're taking the regular function, the f of x function, plotting the derivative. Right? If you want to expand your mind or you're bored on a Wednesday night, ask yourself, how would you do this in reverse? That's what calculus 2 is. Right? You start how to do an antiderivative, which is going the other direction. Starting with this function, how can I work backwards to get that graph? Or from giving the equation 2x minus 1, how can I work backwards to get x squared minus x minus 2? Right? So if you think about it, both directions, forward and backwards, it's like we're learning how to do an all addition right now. And then calculus 2 is going to be, okay, how do we do all that we just learned backwards? Subtraction. Right? So something to think about. And yes, it's really just the power rule in reverse. So you can imagine how we, drop this down and decrease that by 1. Well, we can bring it up and increase the power by 1. Right? We can go both ways and it can work. Right? And there's some other little caveats in there you'll learn when you get there, though. That's something fun to think about. All right, lastly, so we got a couple curves, right? So this is where it starts getting really fun. Anybody want to take a guess? What will the derivative look like here for a third degree function? Yeah, it'll be a parabola. Very good. So we expect a second degree derivative. All right. This is called a cubic function. All right. And our derivative will be quadratic. All right. It will be a parabola. Why parabola? Let's take a look. So how many places have zeros here? 0 slopes. All right, we've got one right here. That has a 0 slope. That has a 0 slope. So there's going to be 2 places on derivative that have a 0. And you know parabolas, they cross the x-axis in 2 places. Right? So at this x value, right here, you're going to have a 0 slope, 0 derivative. And at x equals 1, that will also have a 0 slope. And we can see that if I look to the left of that first 0, these are all increasing, right? These are all positive slopes. So these are the positive slopes up here. Right? These are all positive slopes. So I expect as I approach this 0 slope, it's going to be all positive slopes. And then only right between these 2 zeros, right, these 2 slopes that are 0, now it's decreasing, it's negative. So I expect that part of the graph to be below the x-axis. So that's where you get it coming down here, dips down a little, and then it comes right back up, right? You can see here it's going down, all of a sudden it's back to 0 slope. and then it hits positive again. So it circles around and comes back up, and that's how the parabola is formed. So it's increasing wherever, again, it's above the x-axis. So we have two places where it's increasing. From this point that way, and from this point that way, which correspond to increasing right here. These are all positive slope, positive slope. These are all positive slopes, right? Lots of positive slopes here. So there's two different places where it's increasing. So we'll say this is -1/2. So anywhere less than -1/2 is increasing. That's all these. So as I go this way, less than, where x is less than -1/2, all these are positive. And then also over here, at 1, and as I get bigger, all these are positive. And the only place it's negative is this one little place right here. So I got this much already. X is less than -1/2, x is greater than 1. Just got two of them. And then right between the -1/2 and the 1, that's the only place it's negative, where it's decreasing. That's the only place where it's below the x-axis. So we would say -1/2 less than x is less than 1, which means between -1/2 and 1. That's where it goes down. And if we want to double check this with decimals, we could definitely do that. Just do the power function. Actually, if you just type this in on decimals, f of x equals the function, all you have to do on the next line is just type f prime of x, and it'll give you the graph. It won't give you the equation, but it'll graph the derivative for you, just so you know. But you know how to do the power rule, so you can get 3x squared minus 2x minus 2. All right, try the last one. Make a prediction. What will the graph look like? And why? And go from there. Just trying to build intuition here. And I suppose if you want to make these graphs more accurate, you could find out what the, we know the axis symmetry will be at +1. You could substitute in and find f of +1, -1 plus 3, which is 2, yeah, and find out exactly where the, it'd be in here. Plug in -1 here, find exactly how high it goes. So is it up here, down here? But for now, we can just estimate and say, well, here's where it's positive. These are all positive slopes. Positive, positive. So that's where it's going to be positive slope.